everyone, again welcome to Jnana Learning. So we are continuing with the lecture on electromagnetics, and this is lecture 2, divergence and divergence theorem. So today we are discussing about the divergence of a vector and the divergence theorem. So we start with divergence. So divergence is a very important parameter regarding the vector field. Divergence of a vector field at a given point is actually a measure of how much the field diverges or emanates from that point. Emanates means spread out from that particular point. So we have three cases of divergence, that is positive divergence, negative divergence and zero divergence. So positive divergence means in that case the vector field will be diverging out from the particular point P. That is, the divergence of a vector field at point P is positive because the vector diverges at P. Now in case of negative divergence, here the vector will be converging at a particular point. In positive divergence, the vector will be diverging out, and in negative divergence, the vector field will be converging to the point P, and it is called as a negative divergence. And the third case, it is the zero divergence. So in this case, the vector field will be coming to that point and also it will be going out from that particular point. That is, here the vector is reaching the point, or it is going forward that particular point, but here it is out from that particular point. So the resultant divergence will be, we consider it as a zero divergence. Now the divergence of the field represent actually the rate of change of field strength in the direction of that particular field. So these are the three cases of divergence. Now for a particular vector, the divergence, it is represented as del dot A, or divergence of A, and it is defined as del dot A is equal to dou AX by dou X plus dou AY by dou Y plus dou AZ by dou Z. So that is the divergence of a vector. Now we move on to the physical significance of the divergence. So see, here we are considering a closed surface S. Okay. Now the net outflow of flux of a vector field A from this particular surface is obtained by the integral, closed integral A dot ds. That is, we are considering a closed surface. Now we are considering a vector field A. So the net outflow of the flux of that particular field from this closed surface can be obtained by the integral, closed integral A dot ds. Now the divergence of this particular vector A, it is defined as the net outflow of flux per unit volume over the closed incremental surface. Once again I will explain, that is the divergence of the vector field A, it is defined as the net outward flow of the flux per unit volume. So for a particular volume we are considering, and over this closed incremental surface. So here shown with dotted line, that is the flux of the vector field through the particular surface, this particular closed surface S. Now the divergence of that particular vector at a point P, it is the outward flux per unit volume as the volume shrinks about P. So we can say that the divergence A, that is del dot A, is equal to limit delta V tends to 0. That is for a small volume, we are considering integral A dot ds by del v. So we can write the divergence as limit delta v tends to 0, closed integral A dot ds by delta v. Here delta v, it is a volume enclosed by the closed surface S, where that particular point is located. So that is the physical significance of the divergence, or as a physical interpretation, the divergence can be explained as above. Now we move on to the properties of divergence of a vector field. What are the properties of divergence of a vector field? So the divergence of a vector field, it produces a scalar field. Okay, and for a scalar field, divergence have no sense. Only with divergence we will define it for a vector field, and it produces a scalar field. That is the first property. And the second property, the divergence of a scalar v, that is divergence v make no sense. Then del dot a plus b, which gives del dot a plus del dot b. Now del dot va, which is equal to v del dot a plus a dot del v. And fifth property, that is a vector field whose divergence is 0, is called a solenoidal field. So these are the 5 properties of divergence of a vector field. So that's about the divergence of a vector field. Now we move on to the divergence theorem. That is a theorem regarding the divergence of a vector field. So the theorem states that total outward flux of a vector field A through the closed surface S is same as the volume integral of the divergence of A. That is, here we are relating the surface area and volume of a particular closed surface. That is, the theorem states that total outward flux of a vector field A through the closed surface S, it is same as the volume integral of divergence of A. So if we find the divergence of A and its volume integral, it will be equal to the total outward flux of the vector field A through the closed surface. And this particular divergence theorem is also known as Gauss-Ostrogatsky theorem. And we go for the proof of this particular theorem, the divergence theorem. So for that, we have to consider a closed surface, and it is a volume bounded by the closed surface. So here we have A, the vector field A, and divergence del dot A. Here these are continuous in the region. We consider it as so. And to prove the divergence theorem, we have to subdivide this particular volume into large number of small cells. That is, we have volume V for this closed surface. So in order to prove the divergence theorem, we have to consider that we are subdividing this particular volume into large number of small cells. Now, if the kth cell has volume delta Vk and is bounded by surface Sk, then we can write that closed integral over S, A dot ds is equal to summation over K integral A dot ds, which is equal to summation K integral Sk A dot ds by delta Vk into delta Vk. That is, we are considering many cells, that is large number of small cells. So this summation and this particular integral, we can write this particular integral as integral over Sk, that is for that particular small volume A dot ds by delta Vk into delta Vk. Why? Because as the outward flux to one cell is inward to some neighboring cell, that is, we are considering large number of small cells. So think that the outward flux from one cell will be inward to some other neighboring cell. So there will be a cancellation on every integral of Sk, and it is same as the surface integral over the surface S. Is it clear? As there are many or large number of small cells, the outward flux one from one cell will be the inward to another. So there will be cancellation on every integral over Sk. So that's it. Now in this equation, taking the limit of the RHS and we put it on the equation of the divergence. That is, here we have limit delta V tends to 0, integral A dot ds by delta V. So incorporating these two equations, we can say that is in closed integral over S, A dot ds is equal to this particular expression become integral over V del dot A dV. So that is the divergence theorem. What we have said in the theorem, that is the volume integral of divergence of A. So this is volume integral of divergence of A. Del dot A, it is a divergence, and this is the volume integral of divergence of A. It is equal to the total outward flux of vector field A through the closed surface. That is total flux of A through the closed surface. This will be equal. That is the divergence theorem, and this is the proof for divergence theorem. Hope you have understood the divergence and divergence theorem. So in next class we will continue with curl and the Stokes theorem. So thanks for watching the video. Please do watch all the videos of electromagnetics and subscribe our channel Jnana Learning. Thank you so much.